Well, thank you all for having me here this morning. I'm short, so maybe I'll stand over here. um, thank you for inviting me to come back to the College of Marine Science to talk to you all this morning to kick off your graduate student symposium. I'm over at the USGS St. Petersburg Coastal Marine Science Center, just around the corner. If you've never been there, come by and say hello. We'll be at the Science Festival next weekend, so if anybody's around there on next Friday or Saturday, I'll be around there too. And I've been over there since 2007, working pretty much in the same research group there, studying coastal change and forecasting coastal change. So before maybe I don't know how to use it. Okay, here we go. It's all right. No? Uh-oh. Oh, yeah, we got, it's not on presenter mode or something. Oh, there we go. Okay, so a little bit about me. I guess I already told you I've been over at the USGS since 2007 in the Coastal Change Hazards group. I did my master's degree here, finished in 2010. My advisor was Gary Mitchum. And I'm sure you all know Gary very well. And I had a wonderful experience here. You may notice that I left in 2007, but I didn't graduate until 2010. And so a job opened there and I took it. But maybe my one piece of advice was that is difficult. I wouldn't change it because it's been a wonderful career, but it was hard to work all day and then go home and write my thesis. So I think it took me a little while longer, but we did get it done. And maybe that might be the last time I stood up here on this side of the podium. And so just bring me, like, I have a feeling that I've been here before in a different time, on Groundhog Day. Look, so happy Groundhog Day. It's a little different. I don't think anybody's going to grill me on, derivations I have in my thesis. I mean, you can if you really want to, I guess. I don't remember them very well. Before I came over to do my master's here, I taught high school physics. That was interesting, but yeah, I only did that for 2 years, so not that great. That was a challenging job, which led me to look for a different career. I always loved oceanography, and got my bachelor's degree in physics in Pennsylvania, where there was not really any oceanography. So that's just a little bit about me, my interesting career path. And now we'll go to the science. And I was going to pop up a slide just like full of equations just for fun. But I don't have any equations. I'm not going to do that to you. So I'm part of the USGS Coastal Change Hazards. A lot of people are familiar with the USGS in terms of their natural hazards work, volcanoes, earthquakes, landslides. And so we're sort of this coastal side of preparing and protecting the nation from hazards induced by coastal change, whether that be from storms and hurricanes, from shorelines changing, and from vulnerability to sea level rise. And my work is all in the event scale, the storm impacts, and doing mostly the forecasting of those impacts. And I work, I'm kind of on the operational side of the forecast, and then my colleague on the research side is Meg Palmston. And Meg was a student here before me and did her master's degree with Peter Howd, who was here at the time. I think Pam probably remembers Peter. And then she went on to get her PhD and went all around, and then came back to St. Pete in 2020 to join us again. So hopefully she'll come over sometime and talk to you as well. So let's get into a little bit what is a coastal change hazard? What do you need to forecast a coastal change hazard? Actually, I can go back to this slide. You can see that when you think about a hazard, the hazard is a risk to the people, the infrastructure. That could be homes, roads, water treatment plants, power plants. It could also be an impact to the ecosystem. So we don't only think about, protecting people and lives and infrastructure. We do also think about endangered bird nests, turtle nesting, other things that can be impacted when our coasts change. And we study coasts on all different parts of the U.S. Mostly I study sandy beaches, like here we had Hurricane Isabel in the Outer Banks of North Carolina. But we study coral reef-lined coasts like Puerto Rico. They have a lot of problems, and even cliff and bluff retreat in places like California, Alaska, anywhere in the United States or our territories. We have a mandate to study and predict coastal change. So how do we forecast coastal change? It's kind of simple, and you can do it a number of ways. You need to know something about the offshore forcing. So you need to know the water levels. If we're talking about long-term coastal change, that water level is sea level rise. And if we're talking about event scale, we're talking about tides, storm surge, and the process of wave runup, where we actually have the breaking waves on the beach, which are causing the movement of the sand. And those wave-induced water levels, called wave runup, can be, higher than the storm surge. And that's one thing that was sort of missing from a lot of the storm forecasts until just recently. Sort of that wave-induced water level at the open ocean coast is really important during big wave events. And so then you would need to know, well, what's the elevation of interest for the impact? So we might be curious of the elevation of the base of the dune, where on that photo there you see, the vegetation holding the sand in place. It's been eroded, it's been scarped. If you all go out to the local beach, you probably see a lot of this right now, since they built a lot of really large dunes that don't have any vegetation yet, so they're really steeply scarped. So that can become a hazard, because if your road or home is built on the dune, you're undercutting it, it's going to collapse. Then we might want to know if the water level reaches the dune crest, because then we're going to have overtopping of the dune. We get sand transported landward. It covers the road. That's a hazard to people trying to evacuate. And then finally, we might want to know if the storm surge and sort of the still water level is going to overtop the dune, because now we're going to have, widespread flooding over our barrier islands. So a video did play. Cool. All right. That's wave runup, just in case you don't think about that as much as I do. That's sort of this wave-induced water level that actually gets up and onto the beach and is exacerbated by things like sea level rise and storm surge. Okay, so we do this for the entire nation. So people might do this in small areas. You might want to run a process-based model like X Beach or something like that. But that is, until recently, a little bit too computationally expensive to do for our entire nation. And we really wanted to provide information for the entire nation's open ocean sandy coastline. So a national scale forecast, but with local impacts, so that you could look at the local scale to see what, your forecast of coastal change would be. And so the way that we did this is we had to, you have to make a lot of assumptions when you're going to do something for the entire nation. And so instead of forecasting a shoreline position or a beach volume change, or, we quantify them into these sort of 3 scaled impact regimes. So collision, where we have waves eroding the dune base; overwash, where waves and surge overtopping and transporting sand landward; and inundation, where we have surge over the dune and submerging the beach system. Now, this all depends on a parameterization of the wave runup, because we can't just run like Swan or something and X Beach to get the water level at every, transect along the coast. So we do this in partnership with NOAA, National Weather Service, and National Centers for Environmental Prediction. They, have the operational capabilities. They've got the supercomputers. They're running these weather forecasts and wave forecasts every day, several times a day. And then the USGS adds in the beach morphology piece. So here's how we do the forecast. NOAA forecast is the nearshore wave prediction system, and I don't know if anybody is familiar with that. You might be more familiar with like WaveWatch 3 or something. So it's driven by WaveWatch 3 offshore. It's driven by winds that are selected by the Weather Forecast Office locally. So that's kind of interesting. So they can sort of tune the wind to what they think might be best for their area. And then the water levels are coming from AdCirc, STOFs, or P-surge. During tropical events, the Weather Office can switch over to P-surge if they want to do that, if they think that might be a better forecast. And then they have a really nice high-resolution nearshore waves, and we pull those waves at the 20-meter isobath, so way offshore. And you're thinking, like, that doesn't make sense because you want to know what the water level is on the coast. Because of the shoaling and breaking of waves, it's awfully hard to know what that's going to be. So we use a parameterization that's based on data and observations that uses the wave height and wave period out at the 20-meter isobath and sort of shoals that up to the coast. And it uses the beach slope to turn that into a water level. And the USGS provides the beach slope, and we use the beach slope between the shoreline and the dune toe. So it's like a mean beach slope. And then because you don't know what that beach slope is, it changes seasonally, it changes with events. We also provide an uncertainty of the beach slope. That's our largest source of uncertainty in the forecast. And that's just using back through time and also in a small spatial window, beach slopes that are derived from LIDAR data going back to 1996. So we've got a lot of realizations of beach slope, and every time we get a new realization, we throw it in there. But I'll show you how it contributes to the uncertainty. And then that sort of all gets combined together to give us the total water level and coastal change forecast, which we provide through an online viewer. We provide it to the Weather Service through their own dashboard. So like maybe during, I think it was this recent one, Idalia, locally, they might have a coastal impact statement that would say, hey, we're expecting widespread beach erosion. We're expecting some areas of overtopping. We expect, roads might get inundated. Sometimes they're using this forecast that we work on together. It's pretty cool. And we have an API for anyone who wants to just pull all this data. We have forecasts back to 2016, at least for this local area and North Carolina. And I'll show you how we expanded through time. Okay. Here's our online viewer. It's the little colored dots are each weather forecast office, because this model is run by each forecast office when they kind of see fit. They're typically running it twice a day, but they can run it more often if they want to. And so they run it in the forecast office, run the wave and water level model, and then output that runup, and we ingest it and do the coastal change piece. And so the colored dots tell you sort of the maximum predicted coastal impact in that weather forecast office. This was back in, when did I grab this screenshot? I think it was December, and there was that sort of coastal event that you can see. Tampa Bay is lighting up, and then also Virginia, where we have really low-lying barrier islands. And so you click on your dot for your region, and then you can go in to each alongshore locations, about 500 meters alongshore spacing. And you can then see the forecast of water level. So the dotted line over there is an hourly water level, the still water level, so tide, surge, and wave setup. And then the solid line adds in the wave runup. And that blue envelope is the 95% uncertainty in the wave runup, just solely based on the beach slope variability. So you can see that as we get really large waves and especially long period waves, this sort of uncertainty really blows up. So we know that's oh gosh, go back. Okay, so you would see each colored dot to sort of indicate areas where, like the orange would tell you where there'd be overwash, the yellow is dune erosion, and you can go into your particular area of interest. And then we found that this sort of beach profile resonated with people because they could see the water level going up. And it's not a real beach, it's just a representative profile. So it's got the dune crest height and the dune toe height and the beach slope sort of right. But at least would tell you that today is not going to be a good day for you to put your towel out on the beach because you're going to see the water level is up at the toe of the dune or over it, So, and people are using this forecast for things like, I want to know if my beach volleyball court is going to be wet. So that's kind of cool. We didn't really think of the forecast in this way. We really only collaborated on the forecast for the Weather Service and the weather forecaster. But now we're finding out how people are using it. It's very interesting. I got to talk about that later. Okay, so let's see. There's an example of what this forecast actually looked like on the ground. This is NC12 highway just north of Rodanthe. That highway is not even there anymore. They totally moved it away because this happened all the time. It was a low-lying place. They would try to build these emergency dunes. You can see how effective those were. So finally, they actually just moved the whole road out onto a big bridge. But that's what it looked like during Hurricane Teddy. And then I have another plot that's kind of fun to look at. So this was a forecast for an entire year, 2020. And each dot is an hourly forecast where we predicted that we would have dune erosion or collision. So water level reaching the toe of the dune, and we would have dune erosion. And it's really fun to look at it in this way because you can kind of see from the Gulf of Mexico all the way around to the Atlantic where we have forecasts. We're missing a couple places in the Gulf of Mexico. You can see in space places that are most vulnerable, like low-lying islands on the coast of Georgia. So it kind of doesn't matter what the, surge and wave conditions are. They're sort of always eroding. And then it shows in time. There we go. That's Hurricane Teddy. So Hurricane Teddy remained offshore. It was out in the Atlantic, but it kicked up a lot of large waves that impacted basically the entire eastern seaboard. And that's the kind of event that we really want to highlight with these forecasts because, it's maybe you're not paying attention to Hurricane Teddy. Like, I don't care. I'm not under a storm surge warning. I'm not under a hurricane watch. I'm not paying attention, but this could be a really hazardous day at the beach, And the rip current forecast is almost complementary to this forecast and uses the same wave system. So they're not always coinciding, but they are similar. Okay, so that brings me to the question, how do you know this forecast is any good? So how do you do that? How do you improve it, test it, assimilate data? So I'll show you just a couple ways we do that, just because they're local to this area. So one way we can look at the forecast is through coast cams. So we have a camera mounted on a hotel out at Madeira Beach, and the camera sort of looks down the coast and observes the water level, and we can kind of turn that water level into a time stack here, and then we can digitize the horizontal, the cross-shore extent of that water level, and then through surveying the beach, can translate that into a water level elevation. And then that scatter plot way over on your right shows the hourly observations of water level versus the forecast, and it's pretty good, although we have a little bit of a bias. We're still working on that. So that's one way we can do this, and we have cameras in Puerto Rico, California, Alaska, Guam, Massachusetts. So we're putting one in Louisiana. So we're trying to, obviously we have thousands and thousands of kilometers to validate, but we're trying to at least get different coastal representative conditions to check all of our forecasts. So we also do some other things besides the elevation surveys, which we just do old school, like walking, because we're not allowed to use drones right now. It's okay. That's the camera over there on the Shoreline Resort. We've got a spotter buoy. We've got an ADCP and some pressure sensors. We go out on jet skis and try to survey the bathymetry and just really try to get the most detailed observations at this single site that we can. And just in case anybody wants to grab these observations for your own modeling or whatever, I know you all have plenty of buoys and observations, but we have this one too, and it is transmitting in real time. So that's the website there. Got the wave buoy giving you wave height, period, direction, wind speed and direction, and barometric pressure. And then we can also do sort of an event-based skill assessment where the USGS goes out. The USGS is a big organization, and we have all these water science offices, and they go out in advance of a storm, and they're going to put out these little pressure sensors, little hobos, and they mount them on piers and pilings and hope they get wet during storm events to try to capture water level. And so sometimes we get lucky and they get wet and they capture some good data, and sometimes they're recording at 4 hertz, so that's enough to get waves. And so we can kind of look here during Hurricane Isaias. In North Carolina, we had a NOAA tide gauge out here on the pier. We had a pressure sensor sort of mounted up at the beach, and preliminary observations there indicated there was like 2 meters of wave run up. And it was like, oh, cool, this is where we want to look. Because people were like, I don't believe that. Anyway, it's true. And then so we can really do a good skill assessment. And they had these other pressure sensors. See those little colored dots up there? Those indicate other places where we had observations and forecasts. And then we can, again, just assess the skill of the hourly forecast from the model versus the sensor. And it's pretty good, except for those pink dots at the bottom are during the very beginning of the storm. So maybe we didn't get the timing right of the forecast. So we do this for events whenever we can, like we're working on Ian. I think that's probably the last one we have good data for. And we can also take advantage of observations collected by remote sensing. So we can do look at the LiDAR data, look at difference DEMs, calculate volume changes. This is really good for validating whether we predicted dune erosion properly. We also look at the NOAA imagery that they fly, and we do like an inspection for looking for an inlet, for example, would indicate that inundation occurred. We can look for evidence of like sand transported landward, which would indicate overwash occurred. So we use those observations as well, try to take advantage of any data that's collected. I'm sure you all know this story because collecting data is expensive. So if somebody else does it for us, that's great. And then finally, what's coming new? The areas in green are the newest regions that are coming into the total water level forecast. So a couple places in the Gulf and then the entire West Coast. And then that gray area there, the Florida Keys and Puerto Rico and other reef-line coasts, such as the Pacific Islands, Hawaii, those are going to be added into the forecast. So yeah, the West Coast comes with unique challenges. So those beaches don't look like the beaches on the East Coast. They're rocky, they're steep, there are cliffs. So that's causing a little bit of extra work and research to make sure that we can still do this on a large scale. And then for reef-line coasts, a whole other problem because waves are breaking on the reef. So this open ocean assumption where we take waves at the 20-meter ice about, that's not going to work. So we actually have to do model runs in X Beach, predetermined. So we've got a variety of profiles, we've got a variety of wave conditions, and we're doing sort of like a meta model where we'll have like a Bayesian type lookup table where in real time we can match the wave conditions, the surge conditions, and the profiles to this pre-run model. So that's in the works as well. So different ways of doing things for different areas. Always a challenge. And we're doing a skill assessment for those reef-line coasts, collecting a lot of data in Puerto Rico with those same kind of instruments. And that one has a real-time web page as well, and I forgot to put it on there. So if anybody's working in Puerto Rico, this is in Dorado on the north coast. So we've got, different ADCPs and buoys and cameras there as well. Finally, we're using people to help us improve the forecast, and this has been really a new thing for me. I never, maybe it's something you're thinking about now, but when I started at the USGS, it was like, we have science and we want to share it with you, the public, and so we just went and did what we thought was best. Well, it turns out, maybe that wasn't what people wanted. It wasn't what they needed. Especially, stakeholders like emergency managers who we particularly want to get our science in their hands. They didn't know how to use our forecast, maybe thought it was difficult, or, they want to be able to ingest it into their own system. So now we're learning about human-centered design, doing a lot of stakeholder outreach, and finding out what they want, what they need, what are their questions, and doing sort of, get a first version, go back to your stakeholders, find out what they want, and make something useful, or don't make anything at all. That might be the answer too. It's like, we don't need a tool. That's okay. So we're learning about that, and we're doing that with the weather forecast offices, and they're telling us locations that are priorities for them, where they really want to know the best forecast. These are places that they have parking lots or roads, and so we're working with them to identify, and we're working with the National Park Service, especially on national seashores. Seems like nearly every national seashore is coming to us with these same problems. We have a road, and it keeps getting overwashed, and we keep having to close it. We don't know when to close it. We don't know what to do. What should we do with the road to make it more resilient? And so we're working with them to try to help them, not have these chronic problems again. Like we really can't tell them the solution. We don't do that. We are not a regulatory agency. Thank goodness. We're like scientists, we just get to research things and provide the science, and they get to decide what to do with it. But the stakeholder engagement piece, that's been really fun to see the work that you do being used for a practical application. I think that's it. If there are any questions, happy to take questions, or we can catch up during the break. So yeah, okay, yeah. Thanks, thank you. Oh, sure. Yeah, sure. Right. No, you're absolutely right. And the only reason that we marched around the coast the way we did was just the way that our NOAA colleagues were spinning up the model regions. And that area, it is, I mean, it looks a little different, you're right, and it's low lying, but super important, keeps getting hit by a storm. So we're actually just sort of waiting on our colleagues to get that area running. We have all the morphology data, and we're excited, and we're gonna put a camera, a buoy, and ADCP out on Breton Islands National Wildlife Refuge. So that will be really interesting. It's got some weird wave things going on there. Super weird. So that'll be fun to study. Yeah. Let's see. Oh, got one in the front here.
This may not be relevant since this a lot of like wondering if any of those projects were restoration. How does it affect what you're doing?
Yeah, so that's a great question, and it definitely does. And that's sort of another piece I didn't really talk about of the uncertainty. You know, we can only update our elevations as we have data. And we don't include anything about the nearshore bathymetry if there's an oyster reef or something like that. But we do have people working with some restoration sites in Mississippi and I think also New Jersey, where they're sort of studying the marsh shoreline retreat behind the oyster reefs versus not. And, you know, eventually that will feed into our model, and eventually we'll have it for those areas. But yeah, right now we can't really incorporate it unless we get updated topography. Yeah. Sure.
So you talked a little bit about working with stakeholders to get input on what data products are. I wonder if you guys have thought about going the next step and doing citizen-based science. You know, I mean, you've got citizens throughout the entire region over.
Yes, and we have a little bit the citizen science with there's a thing called CoastSnap, which we don't have around here anywhere, but our colleagues in California do it. And there's a little cradle for your phone, and you can set it in there, and it's georeferenced, and you can just take a picture of the coastline, and then they can ingest that, especially into like shoreline models. You know, we get a realization of the shoreline. So that's one way we're thinking about expanding that. But I think there are other ways too. I think the problem is maybe the red tape. It's a hurdle, but great idea. Yeah.